Hey, welcome to the fourth session on Maths for Data Sciences. So, we looked at probability theory concepts in the first three sessions, and we plan to move towards probability distributions. But before that, I wanted to cover a small topic, permutations and combinations. So, why we need this is basically to understand some of the components of the probability distributions, which we'll be looking at. So this becomes an important concept to understand the probability distributions itself. Now, what are permutations? Permutations are the total number of ways to arrange R items selected from N items. It is represented as NPR or P of N and R. So now to understand the concept of permutation, we'll be looking at an example here. So let us say there are 5 people A, B, C, D, and E who take part in a race. So these 5 people take part in a race, and we have to find the number of ways to get to first, second, and third. So how many number of ways are there so that we can have different person in the first, second, and in the third position in the race. Now the first position, any 5 of them could come in the first position. Therefore, there are 5 ways in which the first position could be decided here. Now once the first position is decided, for the second position we are only left with four possible people who can come in the second position, given that one person has already been given the first position. So there were 5 ways for the first position, but for the second position there are only 4 ways left, since one person is already assigned in the first position here. And now for the third position, it becomes obvious, given that 2 people have already been assigned their positions as first and second, we are only left with 3 possible people who could come in the third position, and therefore the total number of ways here is computed as 3 into 4, 12 into 5, 60. So there are 60 ways. This is the number of permutations for 5 people taken 3 at a time. Now this could also be computed as, let us say we have n equal to 5 here as total population size, and r is equal to 3 as the sample size. Now we are writing the permutations here of 5 and 3 as 5 multiplied by 4 multiplied by 3. So basically there are 3 terms because the total sample is 3 here. Now this can be written as 5 multiplied by 5 minus 1 multiplied by 5 minus 2, which can be written as 5 factorial divided by 3 minus 1 factorial, which is nothing but 5 factorial 5 minus 3 factorial. So basically we are just writing this particular term as 2 factorial here, and this can be written as 5 factorial minus divided by 5 minus 3 whole factorial, which can be written as n factorial divided by n minus r factorial. So now basically we have got a generalized formula for the number of permutations of n items taken r at a time, which is computed as n factorial divided by n minus r factorial. Now since we are considering the positions here as significant, therefore the number of ways we got is 60. But now let us say we are only to compute the number of ways to select 3 items from 5 items. And this is nothing but, this is the total number of ways to select R items from total n items. That is, this is a case of combination. So now what is the difference between permutations and combinations? In permutations, we were selecting 3 items even there, but we were also assigning a position there of first, second and third. In this case, in case of combinations, we are not providing, so no position is given here. This means that we are only selecting any of the 3 items from the total 5 items. In this case, items is the people here. So this is again written as 5C3. Now, how do we compute it? Now, let us say, we'll look at another example. Let us say we have 3 balls. Let us color them something else. So let us say we have 3 balls, the first one being red, the second one being black, and the third one being blue. Now we call these R black, so we just call it BLA and BLU for blue. Now we can also arrange these 3 balls like this. That is, we shifted the black ball to the right and we shifted the blue ball to the leftmost point and we shifted red ball by 1 place towards its right. So now let us say we want to find the total number of ways in which these 3 balls could be arranged in. So let us try to count here. So we have 2 red here, 2 red here and 2 red here. And then let us say we have blue, we have blue and we have blue here, and let's say we have blue at different places, and then for black so we see all these are the only ways in which we can place these 3 different colored balls, and there are total 6 ways to do so. But now let us say we have a lot of colors of balls. Let's say we have 5 color balls now, 5 different colored balls. So how to find the number of ways to arrange them? Now, since we would not want to count in this case because there will be a lot of number of ways in this case, so we cannot really manually count. What we do, let's say we have the 5 positions placed here. Now for the first position, again we follow the same process like we did in permutations. For the first position, we have 5 ways to select the number, select the ball or select the color for the first place. Then there are 4 number of ways left for selecting a color for the second place, and similarly 3 for third place and 2 and 1. Now this will always come out to be the number, the factorial of the total number of colors we are trying to arrange. So the number of ways to arrange, so we can write it in a generalized way now. The number of ways to arrange n items is given as n factorial. Okay, so now that we know this, and we also know the permutations where we were taking r items out of the n selected items. Now in permutations, we have n pr ways to select r items from n items, and then arrange the r items in a particular order. So if you remember the case where we had 5 people and we were having a race competition there, and we were trying to place them in a first, second or third position. So what we were doing is we were actually first selecting 3 people, and then we were actually arranging those 3 selected. So let us say we first select A, B and C as the 3 people who comes in any of the first 3 positions, but then we also have to arrange them in a particular order, because it could be A, B, C, but it could be A, C, B and so on. So now this total combination, both selecting and arranging, we already know there are NPR ways. So the NPR ways, this contains both selection plus arrangement. Now let us say we only want the number of ways to select. So what we do, we divide NPR with total number of ways to arrange, because total number of ways to select multiplied by total number of ways to arrange was the value of NPR. Now this can be written as NPR divided by R factorial, because we already know from this particular derivation here that the total number of ways to arrange n items is given as n factorial, and in this case we are arranging r items, therefore it becomes r factorial. Now taking the formula for NPR from here, we can put it here to get n. This becomes n factorial divided by n minus r factorial and r factorial. And this is the total number of ways to select r items from n items, and this is represented as the number of combinations, which is NCR. So we can write here the generalized formula for NCR as n factorial divided by n minus r factorial multiplied by r factorial. So this is how we get the number of combinations or the number of ways to select r items from a total of n items. So just to recap here, after which we'll move to a particular question, but just to recap what we have learned till now in this particular session. Total ways to select r items is given as combination operator, and it is computed as NCR. Then total ways to arrange selected r items is r factorial, and then finally total ways to select r items and then arrange them is given as NPR, and NPR is nothing but n factorial divided by n minus r factorial, while NCR is n factorial divided by n minus r factorial multiplied by r factorial. So there is this extra r factorial which gets added to the NPR term to get the NCR term. It get added in the denominator. Now let's look at this particular problem here. So on average, how many people do we need in a room to have more than 50% chances that 2 of them share the same birthday? Now let us say we have n people in the room, and we need to find n such that probability of at least 2 people having common birthday is more than or at least 0.5. Now, if you guys remember, we saw something called a complement rule of probability, which states the probability of at least two people having common birthday is greater or equal to 0.5. This means 1 minus probability of no person having common birth date is less than, it's greater than equal to 0.5. So I just replace the left hand side term here by the complement of the probability no person having the common birthday. So if the probability of getting at least two people having a common birthday is x, the probability of no person having a common birthday would be 1 minus x, as these are the only two possible outcomes. Now, changing the sides, this can be written as, so let's call this particular probability as x, the probability of no person having a common birthday. So 1 minus x is greater or equal to 0.5. Therefore, x is less than 1 minus 0.5 and x has to be less than 0.5. Now, why we did this? Because this term is actually easy to calculate. The probability of no person having the common birthday is same as probability of all n people having different birthdays. Now, how do we calculate this particular probability? This is calculated as total permutations of 365 days taken n at a time divided by total number of ways in which we can give a birth date to each of n people. So now how do we calculate this is, why are we using permutation in the numerator here? Because let us say we have 365 days in total. Now let's call these days as, let's say, A, B, C. So A could be 1st Jan, B could be 2nd Jan, C could be 3rd Jan, and so on. We are assuming that there are 365 days. We are just ignoring 29th Feb for now. So let us say we have 365 days and these are called A, B, C and so on. Now let us say we have n people, and since we want a different birthday for each of these n people, there would be 365 days to select birth date for first person. So for the first person, we'll have 365 days to select a birth date. So we can get allotted any of the 365 birth dates to the first person. But now, since we want each of the n people to have a different birthday, for the second person, we will have 364 ways to select birth date for second person, and so on till n people. Therefore, this is nothing but 365 minus 1 and so on. We have n terms here. Now, if you remember, in the case where we had 5 people, so let's color it something else just to separate it. So let's say we had 5 people and we were selecting 3 and race positions. We were calculating this as 5p3 since all the 3 positions were different from each other. So this is a very similar case where we were having, so in this case we were having 5 multiplied by 5 minus 1 multiplied by 5 minus 2. And if you compare it, this particular case from our previous example with this one, you will see it's exactly the same case, but instead of 5 we have 365 days in this case, and instead of r as 3 we have n people in this case. So this can be written as 365 pn, which is nothing but 365 factorial divided by 365 minus n factorial. So this is the numerator now, which is the total permutation of 365 days taken n at a time. Now for the denominator, what we do, so we calculate the denominator. Now in this case we don't have any restriction that each person has to have a different birthday. So there are 365 days for the first person, where we are selecting one of the 365 days for the first person. For the second person also we have 365 days, because the second person could also have the same date as the first person, and so on. We have n terms. So this can be written as 365 raised to power n. So this is actually the total number of ways in which we can assign a birth date to each of the n people here. Therefore, the final probability x, which was so we earlier had x as less than 0.5, this can be written as 365 pn divided by 365 raised to power n less than 0.5. So now this can be either solved using an Excel permutation formula, or it could be computed using Python. So just to mention here, if you want to solve it using Excel, what we do is we use the permute function, which calculate the permutation between any two numbers. So in this case it will be 365. We put an equal to here and n. Now this has to be solved using a hit and trial method. So we put different values of n, and we try to converge to the right value of n based on the answers we are getting for different values of n. And if you notice, the value of this particular expression 23 divided by 365 23, this comes out to around 0.49 something, which is less than 0.5 or just less than 0.5, and therefore we can conclude that n equal to 23 is the minimum number of people required for at least two of them to have a same birthday with a probability of greater than 0.5. So this is how we get the permutation in Excel using the permute function, and we solve this particular problem with a hit and trial method. But the major thing here was to understand how we are getting this particular formula here or formulation here to solve for n now. So this is it from this particular session. Thank you.